which takes into account all these ideas that I have just discussed. So, the example that I have in this case is that of the beam mechanics. So, we consider a beam or a steel rod which is able to, which is flexible, and the beam is of length L, it is of length L and uniform cross section, uniform cross section. The beam is of length L and uniform cross section. Let my function y from 0 to L, from 0 to L to R describe the shape of the beam, and let us say that rho from 0 to L to R is the load per unit length. Okay, or the mass per, or the load per unit length which is acting on the beam, right. So, then in that case the shape of the beam is governed by the functional which minimizes the energy of the beam, right. Now, so it turns out that the shape of the beam y of x is such that the energy functional j y is minimum. The shape is such that the energy functional is minimum, right, and the energy of the beam in general will be given by its sum of elastic energy plus the potential energy, right. We are ignoring the effect of the weight here. Okay. So, the elastic energy of the beam in the most simple notation could be written as a constant. Let me call this as kappa times y double prime square by 2 dx minus 0 to L rho y dy, right. So, my variable here is y here. So, rho y dy. Okay. So, where this quantity in the integral is my bending energy, bending or elastic energy of the beam, and this quantity here is my potential energy of the beam, potential energy, right. Okay. The potential energy, or well, potential energy of the beam due to the load that is acting on the beam. Okay. So, then we need to find the optimal shape of the beam. The optimal shape is such that it is going to first satisfy the Euler-Poisson equation. So, my Euler-Poisson equation for this functional reduces to this ODE. Y fourth derivative with respect to x is rho of, well, rho by kappa, right. Let me call this equation as A, and once we integrate from here, we integrate A, I am going to get that y is equal to y of x is p of x plus set of 4 constants, okay, where my fourth derivative of p of x is nothing but rho by k kappa, right. Okay. So, then, well, this question is how about the other constants? The other constants can be found by our 4 natural boundary conditions that we had just derived, C0 to C3. Okay. Now, to look at, I am going to consider the different cases of these bent beam problems, but to look at that, let me introduce some notations in solid mechanics. So, we introduce certain physical terms or notation in solid mechanics. We introduce the term total force. So, the total force is defined as F is the integral from 0 to L rho dx, right, and this is also equal to from this is from A, this is also equal to integral from 0 to x y fourth derivative kappa times y fourth derivatives of dx, right. Okay. So, then what have I got? From here I can certainly integrate this. This is an exact differential. We see that this is also equal to kappa y third derivative at L minus y third derivative at 0, right. So, this is my total force, right. So, where these quantities here are known as the reaction forces, on the beam at x equal to 0 and L. So, 0 this quantity and at L that quantity. Okay. So, I must say that L comma 0. Okay. So, then also I introduce another term known as the moments, right, moments as well as torque or torque by the force the force above that we had just described. Okay, I call these moments, I denote them as m, right. So, the moments are denoted by m, where m is integral 0 to L x times rho dx, right, or this is from A, I get that this is also equal to kappa times integral x y fourth derivative dx from x 0 to x 1, right, well, from 0 to L. Okay. So, I see that this is also equal to kappa of, we do the integration by parts and we are going to come to a fact that this is also equal to L times y triple prime at L minus y double prime at L plus y double prime at 0, right. Well, again we have this time we have these quantities as my reaction forces, and this quantity is the moment produced by the reaction forces, Okay. So, then let us now look at some special cases of these beam problems, namely the different examples where the beams are either clamped or freely moving. So, let us look at the simplest case. The first case, we can have a beam which is doubly clamped, or the beam is clamped at x equal to at x 0 and at x 1. So, which means that we have a fixed boundary at x 0 and x 1. So, this is my standard fixed point boundary condition problem. Let us say we have the boundary condition of the form. So, let us say x 0 is 0 and x 1 is L. So, y prime 0 is equal to y of 0. So, the y coordinate as well as its slope at 0 is equal to the y coordinate as well as its slope at L is equal to 0. So, this is the standard. We approach in a standard Euler-Poisson setup with only fixed point boundary conditions. Then we could also look at, so that is already been done quite a few times. The second case we have in mind is the cantilever problem. Cantilever case where the beam, where we have a beam, let us say this is my horizontal, the beam is able to bend at one of the endpoints, right, So, this is my fixed boundary here. So, at x 0 equal to 0 the beam is fixed as well as its slope is defined, but on the other end at x 1 equal to L it is free to move, right. So, it means this is a situation where the beam is clamped at x equal to 0, or I have that y of 0 is equal to y prime 0 is equal to 0, right. So, then so these are my two boundary conditions, the fixed point conditions, and my other two boundary conditions at x equal to L are my natural conditions, or at x 1 equal to L I have the natural condition. We impose the natural boundary condition that I have del f del y double prime. Let us go back a few slides. We have the natural boundary conditions which are these two quantities at x 1, right. So, at x 1 I have del f del y double prime, and f, what is f? F is my quantity which is kappa y double prime square by 2 minus rho y, right. So, my function f, the integrand is kappa by 2 y double prime square minus rho of y, right. So, this is my quantity f. So, partial f partial y double prime is equal to kappa times y double prime evaluated at, this is the condition only imposed at x equal to L, right. So, I get that kappa of y double prime L, this is equal to 0, right. So, there is no reaction moment at x equal to 0, right. And then we also have the other boundary condition being satisfied at x equal to L, which is d dx of partial f partial x y double prime minus partial f partial y prime at x 1 equal to L, which is also equal to kappa times y triple prime at x equal to L, which is set equal to 0 here. Okay. So, this one is my reaction force. Okay. So, these are my reaction force. Okay. So, then we now have 4 boundary conditions and the problem now is fully defined. So, let us continue with another case. Suppose we are given a beam which is just supported over a particular support, right. So, suppose we have a setup that if a beam is, let us say this is my point x 0 which is 0 and this is my point x 1 which is L, and suppose I have a beam which is, let us say, supported at these 2 points, then this question is how are we going to find the extremal shape of this beam. So, again, so the case is simply supported beam. So, how to approach? For simply supported beam, we will certainly have that the fixed point condition y at 0 and at y at L, they are set equal to 0. So, certainly we have 2 fixed point conditions. So, 2 fixed point conditions given by y of 0 equal to y at L is equal to 0. However, note that in this case the slope may not be 0 because it is just a simply supported beam case. So, for the slope we are going to, instead of the fixed slope, we are going to use the natural boundary condition for the to determine the slope at these endpoints. So, the natural boundary condition would be that the reaction moments and the reaction forces are set equal to 0. So, we have the following. So, for slope at the endpoints, to specify the slope at the endpoints, we instead replace with these two conditions. We have partial f partial y, the first set of condition out of the 4 at x naught and x 1, this is equal to 0, right. So those are my set of 4 boundary conditions for simply supported case. Then finally, we could also include a case which is the unsupported beam. The unsupported beam is where neither the position, so unsupported case, where neither position nor the slope, neither position nor the slope is specified, right. Neither position nor the slope is specified. So in that case, we can use all sets of 4 natural boundary condition. So use all 4 natural boundary condition, which are the following. We have the reaction moments set equal to 0. So the double primes are my reaction moments, y double prime, y at 0 and L is 0, that comes right from this set of condition here, right, and my reaction forces are also 0. Okay. So those are my 4 sets of natural boundary condition, and that will complete our problem description. Okay. Finally, we have one more case, and we will see that this is not solvable by the model that we have just described. The case that I have is with a beam having only one endpoint fixed, but not clamped, right. So what is this scenario? We have a beam, let us say the beam has one endpoint fixed. So x 0 equal to 0 has a fixed coordinate y 0, but the slope of the beam at this point is not defined. So in this case, y prime at x 0 also is unknown, right. So what should we expect that the beams, what would be the optimal shape of the beam in this case? Well, the beam is free to move, except that the position is fixed at one point. So the physics tells us that the beam will just lie into a configuration which is parallel to the wall, or to reduce the total energy of the beam, and this is a case where the model has failed. The model cannot justify this configuration of the beam. It is purely coming out of the physics, right. So the model fails here because the beam collapses and lies vertical. The beam collapses and lies vertical. So there is no solution, right. Okay. So let us look at another example. So to consider another example, we need to revisit our assumption on the elastic energy of the beam. So let us reconsider our beam example, and especially the elastic energy of the beam in our beam problem. Notice that the elastic energy that we have chosen was of the following form: kappa times y double prime square dx, right, where kappa was assumed to be a constant, right. So this was our elastic energy of the beam, but this is when the slope, when the beam bends, the bending of the beam is negligibly small. This is true only when the slope is very small, right. we will see once we derive the general. Well, so this is nothing but the curvature of the beam. The curvature decides the elastic energy, right. We will see that when we derive the general expression for the curvature, in general the curvature depends on the slope of the shape of the beam, right, and it again reduces to this following form when the slope of the beam is very small, right. So in general, I have kappa of S. Kappa of S is the line curvature or the curvature of the curve of our interest, and this is also equal to the magnitude of the rate, at which the tangent of the arc length changes. The tangent of the arc length changes direction, right. So it is also the magnitude of the rate at which the tangent of the arc length changes direction. Okay. So what exactly is kappa of S? So kappa of S is the magnitude of the rate of change of the tangent, the rate at which the tangent changes. So the tangent of the curve is given by r dot of S, and the rate at which tangent changes is r double dot of S and its magnitude, right. So this is nothing but, so in 2D, this is nothing but the magnitude of x double dot comma y double dot of S, where the double dot is of course the derivative of the quantity with respect to the independent variable S being the arc length, or this is also the magnitude is also equal to the square root of x dot square plus y double dot square. Okay. So where we define my dot to be the derivative with respect to the variable S or the arc length. Now we need to describe all these derivatives x double dot and y double dot. Note that my arc length of the curve ds will be such that this is also equal to dx square plus dy square, right. So my ds square is dx square plus dy square, or I get that dx ds dx whole square is equal to 1 plus y prime square, right. From here I get that ds dx is equal to square root of 1 plus y prime square. From here I also get that dx ds is 1 by square root of 1 plus y prime square, right. Okay. So what we have is the following. So we have found out the relation, so we have found out the expression for the derivative of x with respect to S or x dot. So this is also equal to my x dot of S. So from here I can find x double dot by differentiating this quantity one more time. So my x double dot of S is the derivative of x dot with respect to S. I can do a chain rule that this is also equal to the derivative of x with derivative of x dot with respect to x times the derivative of x with respect to S, okay, or this is also equal to, so this quantity is x dot of S times the derivative of x dot with respect to x is going to give me, so well, x dot was this quantity. So I am going to differentiate this quantity. I get that this is also equal to x dot prime, where the prime denotes the derivative with respect to x, right. So I get that this is also equal to x dot is 1 plus y prime square under the root, and the second one is the derivative of this quantity, okay, or After simplification, I get that this is also equal to minus y prime y double prime divided by 1 plus y prime square whole square. Okay. So, similarly I can find y double dot of s, right. How should we do that? We know that what do we know? We know this following relation. We know that from here I know that x dot square plus y dot square is equal to 1, right. You can divide throughout by s. Okay. So, from here I can find y dot, and y dot turns out to be, so we know that x dot square plus y dot square is equal to 1. We already know x dot, we plug it and we find that y dot of s comes out to be y prime divided by square root of 1 plus y prime square. Okay. So, y double dot of s again using chain rule will be x dot of s times y dot of s the prime. Now, the prime is nothing but the derivative with respect to x. Okay. So, once we substitute all these expressions, I am going to get that finally y double dot of s is coming out to be y double prime divided by square root of not square root y double prime divided by 1 plus y prime square of whole square. Okay. So, that is what we get. Okay. So, finally my curvature kappa of s is x double dot plus y double dot square plus y double dot square, let me call this as kappa square, and then we use these two expressions that we have just derived to come to the conclusion that this turns out to be, after plugging in all the values, I get that this is also equal to y double prime square divided by 1 plus y prime square to the power 3, right. Or my curvature, notice that my curvature now depends on the slope of the curve y prime, and it reduces to y double prime square for when the slope is negligibly small. Okay. Right. So, what have I said is the following: for small deflection, I have y prime equal to y double prime by 1 plus y prime square to the power 3 by 2. This is also equal to y double prime of 1 minus 3 by 2 y prime square plus order of y prime 4, right. Note that now my curvature so this is my curvature now. So, my kappa of s, taking the square root of the previous result, my curvature comes out to be y double prime plus some higher order terms which will vanish if the slope is small, right. So, we are going to look at the class of beam problems from now in this lecture, where we minimize the elastic energy, and those class of beam problems with minimum elastic energy are known as Elastica. So, we are going to look at the shape of Elastica for different setup. So, bent beams with minimum elastic energy are known as Elastica. Well, typical example is a thin strip of metal which adopts a shape when forced to bend, right. A thin strip. So, example is a thin strip of elastic material material which adopts so the shape. So, elastica is the shape, it is the shape of a thin strip of elastic material which is adopted when forced to bend, Okay. So, we are going to look at two examples of elastica. So, the elastica